Hey, Year 12s, welcome to Monday's further math lesson. Today we're going to take a look at exercise 9.3, which is on communication and dominance matrices. Now, all communication diagrams are basically a way to show the connection between different points, different cities, could be computers, could be people. Now, we're not going to talk about dominance matrix today. We're going to talk about that on Thursday because once you understand communication, the dominance matrices are quite straightforward. So here we've got a little diagram. It looks like the diagram is talking about computers. And we've got computer A, computer B, computer C, computer D. All it means is if we take this line from computer A to computer D, for example, we can represent this diagram as a matrix. We can say, well, this line from A to D is this element here in the matrix diagram. So from A to D, we've highlighted the 1 because there's one connection from A to D. If there's no connections, we write 0. And as you can see, there's all these other 1s in the matrix. These represent the corresponding lines that travel between the 4 computers. Let's put this to an example so we can do some hands-on ourselves. The first example talks about 4 cities: Arcton, Brenton, Corkton, and Dunton, indicated by their first letters. We've abbreviated to A, B, C, and D. These are talking about the airlines that fly direct between these 4 cities. So if we look at our matrix communication diagram, we can see here all the 0s and 1s. Whenever there's a 0, there's no connection. Whenever there is a 1, we have to draw a line. So let's take this one here, for example, from C. So from Corkton, we can fly to Arcton. So this means we can go from C to A. Like so. The arrow is really important. You got to point it in the right direction because sometimes you might not get a flight that comes back the other way. Let's take a look at the next one from left to right. We've got Arcton. From Arcton, we can fly to Brenton. From Arcton, we can fly to Brenton. From Corkton, we can fly to Brenton as well. Remember, these lines can draw it however you like. Ideally, just keep it straightforward until there's looping connections later on. But I mean, there's no issues if you want to draw a big loop. It's just going to hurt my brain when I mark this X. From Dunton, we can get to Brenton as well. So D to B, we can draw a little line like so. From Arcton, we can get to Corkton, so A to C. What we can do is we can just draw a little arrow on the initial path. So there's return flights from A and C. From Dunton, we can also get to Corkton. So from Dunton, we can fly to Corkton. From Brenton, we can fly to Dunton. So from Brenton, we can fly to Dunton. That means we can put an arrow like so. Right, that's our diagram, our communication matrix diagram complete. The next part B, says evaluate the matrix product N equals matrix K times matrix M, where matrix K is a row summing matrix of 1s. If we take a look, matrix N is up here, which is the communication matrix we just did for our diagram. What we need to do is we say, well, N, matrix N here is going to equal matrix K. So if this is our matrix K, we have to times matrix K with matrix N. All right, and if this is our matrix M, all right, if you put that into your CAS in this exact order, so notice how it's K times M. If it was in the other order, it'll be invalid because the matrix orders won't match. What we get is then matrix N. Okay, so if we call matrix N in green, we can say, well, we've got a matrix, a row matrix of 2, 1, 2, 2. What does this mean? what you notice is every time you use a row summing matrix, you're adding all the columns together of the standard matrix. Here we've got the communication matrix M. So the 2 here is the 1 plus 1, got us 2. The 1 down here is the 1, the second column. The 2 in the third column is the total of the third column of matrix M, so on and so forth. All right. And that's what question C says. What effect has pre-multiplying K, so remember K is a yellow matrix, on M, which is the communication matrix, and what information does matrix N contain? So as we were saying, matrix N tells us the total of each column's values. So matrix N here sums the columns of matrix M. This shows us the number of direct flights out of each city. Okay, so for example, this 2 here tells us there's 2 direct flights out of the city of Arcton to the other 4 cities. All right, so on and so forth. So there's 1 flight out of B, 2 flights out of C, 2 flights out of D. Which city has the fewest direct flights to the other 3 cities? Well, this one here, City B only has 1 direct flight. So if we underline that, okay, the 1 direct flight is correlated to, or corresponding to, sorry, the B in the communication matrix. Hopefully this is making sense so far. Remember to comment down any questions below or email through. I'm sure other people will have the same pressing questions. Communication matrix 2 example. We've got 2 sets of very similar matrices. If you pause this video, take a look at what you think is different, or can you spot the difference? Right, if you said that I has different arrows compared to double I, well, you're correct. So notice how here D can fly back to A in this second part, whereas in the first part, D cannot fly back to A directly. Then if you said that, you are correct. So find the communication matrix M that matches each communication diagram. So what I've done here is I've gone ahead and filled out the matrix for you guys like so. How we got these numbers, for example, the first part is you got to draw the structure. So the rows, or well, the part up top is always going to be from. The part on the side is always going to be to. You want to make sure above your matrix block you have A, B, C, D, E, or however many nodes there are. And on the side you write matrix M, because the question here says find the communication matrix M. And that's important later on because we call this matrix M as a reference point. So let's get to it. How did we get this B from B to A? From B to A is this line right here. Okay, and what you notice is that goes both ways. So from B to A and B to A, these come from the following line. All right. Another one, I won't do all of them because it'll be too tedious. I think you get the gist. This E to B line and back to E to B. Okay, you've got from E to B right there, and from B E to B. So, sorry, what did I say? From B to E. Okay, these ones correspond to that line there. This singular line, A to D, there's only one. So A to D, that's why there's a 1 there. All right, so fill out all the ones, and then once you're done with all the lines, that's when you can patch up all the zeros. All right, what you notice here is there's 2-way lines between each point. And what that means is you're going to get a symmetrical matrix. All right, so using what we did before, this line here, A to D, I'll just show you. Instead of just having one value down here like before, A to D now, well, we can go from D back to A. So that means now there's a 1 there compared to the previous where there's no 1 in that element spot from D to A. Okay, so that's going to be the main difference. Everything else, how we fill that out, is going to be the exact same process as what we just did before. Part B, explain why the second communication matrix is symmetrical about the leading diagonal. So if we're just talking about this, notice how the diagonal is 0 because there's no looping path. Like, it'll be a bit silly to communicate sometimes with yourself. So if we were to fold this matrix along this diagonal, you're going to have an exact replica. So these 2 1s here are symmetrical with those 2 1s. These 2 1s here are symmetrical with these 2 1s, so on and so forth. And so if you could just visually imagine us folding these 2 corners together, okay, along this diagonal, we get a symmetrical matrix. All right, and that's what it's talking about. Okay, because the diagram has 2-way communication arrows. That's always going to be the case. Part C, this diagram shows the driving times in minutes between 4 towns. Write a matrix that represents this information. So your first step is you got to draw the matrix diagram, so the box, and then you got to have A, B, C, and D on the top, A, B, C, and D on the right side. The top is always going to be from, the right side is always going to be to. We're calling this matrix, well, we can call it anything you like. It doesn't say, so I've just called it matrix M again. And what you notice here is it's saying from A to A. Well, there's no connecting line that's a loop that's going from A to A, is there? That's why that's a 0. From B though to A, so from B to A, it takes 23 minutes. Remember, we're talking about minutes here. So from A to B, this road would take 23 minutes. And that's why we've got the 23 there. And because it's a road, you can go back and forth on that road, right? The road has 2 ways. So that's what's implied when it talks about towns. Okay, it implies that you can go either direction. So that means the 23 can also be from A to B and from B to A. That's why we've got the 23 path like so. We're not going to do all of them like again, it'll be just too tedious, but let's take C to D, for example, or D to C. This line here, from D going to C would be right there. From C going to D would be this element right there, right? And then that corresponds to those lines. And you would fill out the rest like so, and you'll notice that there's no looping roads that take you from A back to A. That's kind of pointless. So that's why you've got a diagonal column of 0s. What are multi-step communications? I think for these sort of stuff, you can come back and read this once we do the examples. It's better to learn multi-step through examples, in my opinion. So we're going to push on and talk about multi-step communications. So if we had a diagram like so with 4 points, A, B, C, and D, a multi-step connection or communication can mean, well, if it's 2-step, even though we can't get from A to B in 1 step, we can actually get A and B in 2 steps. We can take A to D first and then D up to B. And that works as a 2-step communication, right? So it's sort of your degrees of separation. You can also go 3 steps. So for example, let's just take a look at the examples first before I can't think of any on the top of my head. But what we have here is, on the right, we've got a matrix that shows the 1-step connection between each line or each point. Okay, so from A, we can get to D and we can get to C. All right, but we can't get to B and we can't get to A. All right, there's no looping line, and so on and so forth. The question asks us to produce a 2-step communication matrix. And what we have to do is, you can do this in your head if you really want to multiply the matrix yourself, or you can just use the CAS and take the original communication matrix, the M, and what you do is you type this into your CAS. So this matrix here is just M. and power it to 2. So whenever it says 2-step, you power it to 2. If it's 3-step, you power it to 3, so on and so forth. And what we create is a new 2-step matrix. So what this matrix means is from A, in 2 steps, we can get back to A. From B, in 2 steps, we can travel to point A. So let's analyze that. From A, if we were to move twice, we can get back to A by going to C and then back to A. From B, we can get to A by taking 2 paths. So going from B to C and then C to A. So that's how we've connected B to A in 2 steps. So this is just talking about exclusively 2-step communications, okay? Not 1 step, not 3 steps, just moving twice, okay? You can get from the cities with a value that's not 0. In double I, the number of 2-step self-communications from A to A and list all paths. So what I've done is I've just copied the diagram from above to show you how we go about it. Now, if we look in our 2-step communication matrix, we know there's one path that exists, okay? That's A to A. All right, so from A to A, if we were to highlight this like so, from A to A, we know from the matrix above, there's definitely one path. Which path is it? This path here. We go to C and then we go back to A. All right, so we start at A and then we go back to A. I don't know why I wrote C there. That's a typo. Let's fix that. And back to A. Right. So notice how it's 2 steps. We've got 2 arrows, and people go, well, why do we have 3 letters? This is our start and finishing point. Okay, the steps are the arrows. Okay, so the steps are always going to be the arrows. The number of 2-step communications from A to B. So from A to B, we've got 2. And that's how we got the 2 paths. Okay, from A to B. Let's just highlight this. Remember, the question says for us to list the path as well. So what we have is the first path, A to D to B. So we go from A, we could go from A to D to B, or we could go from A to C to B. Ah, boy. Or we could go from, let's try this again. Oh, let's use green. A to C to B. So A, we go A to C and up to B. So those are the 2 ways that's shown in the communication matrix above. And we've listed the path. Next one says the 3-step communications. So if we were to move, so that was 2 arrows is 2 steps. If we were to take 3 paths, what we need to do is we take the original M matrix, so this matrix up here, and we power it by 3 using the CAS. And what we've done is this shows us the 3 path connection between each point. So we can get from A back to A, okay, with one of the 3, with one 3-step path. We can get from C to A in 2 3-step paths. And let's take a look at what the paths are. So the question in double I says the number of 3-step self-communications from A to A. Well, if we go back to our matrix up top, A to A, so starting from A back to A, there's one path. That's how we got the one path. Which path is it? We need to take a look at our diagram. Well, if we were to start at A and finish back in A and we can only move 3 times, the only way is to go from A to D, D to C, and then C back up to A. So notice how we've gone 3 times. And people might be like, Ed, how do we figure this out? Trial and error. Yep. So just use your observation. Part 3, the number of three-step communications from C to B. So from C to B, there's 3 of them. So from C to B, there's 3 paths. All right, so that's how we got our answer of 3 paths. And what we notice is each one's going to start at C and finish off at B. So we can get to B by going C, A, D, B. So C to A to D, and D, oh man, start that again. So C to A to D, D to B. And that's 1, 2, 3 steps. The other way you can get to B in 3 steps from C is C to A to C, and then to B. So you can go C to A, back to C, and then to B. And people looking at this diagram might go, well, that's only 2 steps, but you've actually gone up to A and then back to C. So that's 1, that's 2, and that's 3. The last one here, you've got C to B, B to C, and then C to B. So you can go, C to B. Okay, that's not going to work, is it? With the highlighting overlaps. So you can go C to B, back to C, and then back to B. So that's 1, 2, 3. All right, so that's commonly one of the ones that people usually forget, that you can go back and forth, which is pretty disturbing because, you know, sometimes you'll find the first 2 parts pretty easy and then you're like, well, where's the 3rd part? And just remember you can go back and forth. So that's kind of mind-boggling at times. Part C says, in either matrix that shows the number of 1 or 2-step communications. If you ever see OR, that means we add the 2 matrices together. So matrix 2-step communication, or matrix M squared, this matrix came from up top in this example here, back in example A. So we've taken that matrix and we've used it in example C, and then this one was at the very beginning of the question. Okay, so we've collected the 2 matrices from previous questions, and what we've done is we've added them. So you add each element that's corresponding to each other. So here, 0 plus 1 gets us 1, or you could do this in the CAS if you think it's quicker. I mean, it's up to you. Some people might add quickly in their head. Some people might type it in quicker in their CAS and adding. But here we've got 0 plus 1, that gets us 1. 1 plus 0 gets us 1. 0 plus 1 gets us 1. 0 plus 2 gets us a 2. 0 plus 1 gets us a 1, so on and so forth. I think you get the gist. But once you've got this final matrix, make sure you put the letters up top and on the right, and write from and to, like always, with these communication matrices. Because ultimately, the matrix won't mean a thing if you don't label the matrix itself in communications. Part 2 of section C says the number of 1 or 2-step communications from D to C. So from D to C, from D to C, we know there's 2 of them. Okay, and this means you can either take 1 step or 2 steps, up to you. Okay, but no more than 2 steps. So the first one here, D to C, pretty straightforward. We can just go from D to C like so. Or you could take a 2-step and go from D to B and then to C. You go D to B and then to C like so. And those are the 2 paths that correspond to this matrix that was created from us adding matrix M and matrix M squared together, which is a 2-step and the 1-step. Triple I says the communications that can't be made with either 1 or 2 steps. This is when we take a look at the zeros. All right, so we can see there's zeros from B to D and from D to D. If you see zeros, we can't connect the two in 1 or 2 steps because, well, this is 1 step, this is 2 step. So there's no 1 or 2 step connections. Right, and that's how we ended up with that stuff there. Okay, I've just copied across this this matrix from up top. Section D, the matrix that shows the number of communications of no more than 3 steps. So now we have to add the single step separation, the 2-step separation, the 3-step separation or paths together, and it's just the same. You go each corresponding element and you add it together. So 0 plus 1 plus 1 gets us 2. 0 plus 1 plus 0 gets us 1. 1 plus 0 plus 2 gets us 3. Or you could do it in your CAS and punch in these 3 and replicate it in the CAS scratchpad to create the no more than 3 communication matrix. This, okay, always needs to be labeled. So up top from, on the side to. Without these labels, again, you can't get full marks. Part II of the section D says evidence that every one of the 4 computers can communicate with every other computer using 1, 2, or 3-step communications. Well, the evidence is there's no more zeros left. In our previous matrix up top with the 2-step, we couldn't get from B to D in 1 or 2 steps, or D back to D in 1 or 2 steps either. But in 3 steps, there is a path now for those 2 elements. And so this means they're all connected because there are no more zeros in the matrix. Yay, so every computer can communicate with each other. Or every city, every whatever the question will end up to be. That's all for today. Okay, remember for exercise 9.3, just do the ones that say communication for now, and then on Thursday we're going to talk about the ones for dominance. Okay, I promise the dominance one won't be as long, it'll be nice and quick. Thanks everyone.